So our final chapter is chapter 9, and this is mathematical modeling. Most things will look familiar. We're going to deal with linear models and exponential models, and we've seen both of these in chapter 8. Only now we're going to take this in a more general exponential modeling format, and we're going to spend a little bit more time comparing exponential models to linear models. So the basic exponential model is given here. Q, some population, is equal to Q naught, or Q0, some initial population, times 1 plus R, which is a growth rate or a decay rate. If it's a growth rate, it's positive. If it's a decay rate, it's negative. Raised to the power of T, where T is some measurement of time. Depending on the problem, that'll be days, weeks, minutes, hours, just whatever the problem tells us. So, our first example involves the U.S. Census from 2010. Found that the U.S. population was about 309 million, had an estimated growth rate of 0.09% per year. It asks us to write the population for the U.S. that assumes this growth rate and uses this equation to predict the population in 2100. So we've got two tasks. First, let's write the equation for the U.S. population with this rate. So maybe the first thing to note, our initial time is the year 2010. Okay, our beginning of this entire thing. When the population was measured in that time, Q naught was 309 million. Million is 10 to the 6, so in scientific notation, that's 309 million. 309 times 10 to the 6. Now, our model, the first question we're asked to come up with is, what is our population Q given any time t? That's equal to Q naught, the initial population, times 1 plus R to the t. This model is not complete until Q naught and R are filled in with numbers. T will remain T. It's a variable. It'll be part of our formula to predict in the future with. So we know one of these things so far. We know Q naught is 309 times 10 to the 6. There's Q naught. And then that's times 1 plus R to the t. Well, we have to ask ourselves, what is R to the t? Well, if we go back up into the problem and look, 0.09% per year, that's a growth rate. So we'll just write R down as 0.09% positive, because it's a growth rate. Convert that to a decimal, 0.0009, and that's what we write into this formula. So our model is essentially a formula that predicts for any time t what the population will be Q at that time t. Okay, so let's see one round of using one of these models in this situation. The question asks us to predict the population in the year 2100. Okay, so the time t that will elapse is whatever year we're in, which is 2100 that we're interested in, minus where everything started, 2010, that's 90. So then the population in 2010 is Q of 90, which really just means we plug 90 into our formula where we see a t. This is what a model does. Lets us predict based on time or other independent variables. 1 plus 0.0009 is this. We're raising this to the 90th power. We're using this model now to predict a population or approximate a population 90 years into the future. And once we plug all this into a calculator, let's see this one time around. This is 309 million, that's 6 zeros, times 1.0009. Raise this number only, 1.0009 to the power of 90, and we get 335,058,401.3. So let's write that down in our problem. And we have 335 million. We can convert it back to scientific notation, but if we want to carry out all these significant figures, we can also do this as well. 401.3. The question doesn't tell us to round to any specific value, so we'll just leave that decimal as we have it and just say that it's an approximation in general. Okay, so there's our first exponential model. It's a growth model. Notice that the population started at 309 million, and 90 years later we saw that it was 335 million. So let's see a decay scenario. So maybe we have a population that's shrinking in size. So this example tells us that a country's population declines at a rate of 0.06%. So maybe this time we'll recognize the rate right away. It's a decline, so it's negative 0.06%, and converting this to a decimal is negative 0.0006. Now what is Q naught? We're looking for more. Write the equation for the exponential decay of the population, so further instruction, just like the previous problem. Use that to predict what a population of 1 billion people will shrink to after 60 years. So there it is. Q naught, the initial population we're interested in, is 1 billion. That's 1 times 10 to the 9th. Remember, 10 to the 9th is 1 billion. And T is 60 years. Okay, first they want us to form the equation, the model. In other words, fill this out all except for T. T is just going to be itself. Q naught times 1 plus R to the T. Okay, so in this model, well, it'll be complete once we know Q naught and once we know R, and T will again just be itself. Then we'll do a prediction with it as the problem asks. So Q of T, we know that Q naught is 1 times 10 to the 9th. Well, it's really just 10 to the 9th if we want to be short about it. Or you can write it as 1 billion, which is 1 with 9 zeros behind it. This saves a little bit of space. 1 plus negative 0.0006 all to the T. We just need to combine 1 and that negative decimal. So Q of T is equal to 10 to the 9th times 0.9994 to the T. This is our exponential model for the decline of this population. If the population has a constant decay rate of 0.06%, then this equation will tell us for any time T years down the road how many people are left in that population. So they ask us to approximate the population at 60 years. Population after 60 years. So this is just simply 60 years later. T is measured in years because it's 0.06% per year. So this is Q of 60, and that's 10 to the 9th times 0.9994 to the 60th. And this, once we plug it into a calculator, very similar to what we did in the previous problem, we get 964,629,871, and we have a decimal of 0.3. It's sort of trivial, but we'll throw it in just because we know it. So again, same scenarios happen. First we built a model, then we use that model to predict some value of the population or whatever it is we're modeling exponentially in decay or growth sometime in the future. So that's the basics of these exponential models, these general exponential models with rate R and initial population Q naught. In the next video we'll do a more involved linear versus exponential comparison.